This is my sweet friend, Poole, and he is a genius when it comes to mathematics, calculus, and all kinds of things, numbers. And he's an outstanding trumpet player with the All-American Band. And yesterday, he was telling me some fascinating facts regarding Honeycomb. So I'll let him fill you in.
Okay. Well, I'm not a genius trumpet player, but I do love playing the trumpet. And I'm not a genius math teacher, but I do love math. And I've been studying bees for years. When I was an undergraduate studying, a professor showed me two papers that were published by the National Council of Teachers of Math in their journal in 1969. And the gist of these papers, the title of one of the articles was Mathematics of the Honeycomb. And he used it to introduce the subject to calculus. So when I started teaching calculus at United Christian Academy about 8 years ago, I decided I'd use the same thing as a review of pre-calculus. So it's really a pre-calculus problem. So the basic idea is to study the way the bees store honey. And they store honey in hexagonal shells. If you've ever seen a honeycomb, you know they make millions of cells. They're all the same shape, and they're perfect little hexagons. But they don't have a square back like you would think. They have a special side that has three planes that intersect. It's called a trihedral base. They're really rhombuses, and they're regular rhombuses. Their sides are all the same. And so the math exercise is to derive an expression for the surface area of this hexagonal cell. And the idea is if you were an engineer and you were designing these storage cells, you would want to minimize the cost of building them, which is, for the bees, it's making wax. They make a lot of wax. So the back of the cells, it's tilted, and the tilt can be very flat, or it can be very steep, or it can be somewhere in between. And the question is, what would be the best side? So when you make these cells, you can make them by making a cut of a certain depth, and we call that variable. That's the x, the unknown. Everything else is determined by the shape of the bee inside the bees. But that depth of cut is up to the bees. They decide whether they want a long skinny back, or whether they want to make it just flat to make their life easier, or whether they want to come out somewhere in between. So we derive this equation, and it's six rectangular sides, 6 triangles. But the rhombuses are a little tricky, and they involve using the Pythagorean theorem, a squared plus b squared is c squared, and a little 3690 trigonometry. So it's a nice review of a lot of pre-calculus topics. In the end, you get an equation with 3 parts: the six rectangles minus 6 triangles plus 3 rhombi. And the 3 rhombi is a radical expression, so it's a square root, and under the square root is something like s squared plus a squared. X squared plus 4x squared plus s squared, where s is the side length, that's fixed, and the 4x squared, that's the variable. All that radical makes it a little bit hard to go to the next step, which is to figure out how do you minimize that formula. And it turns out we use what's called a difference equation, and so the algebra gets messy, and when we do it in class, we fill up the whole board with this expression. But in the end, you end up learning about what a derivative is. And so what you do is you let the change in x go to 0, you take the limit, and you get the derivative of this equation. When you take the derivative and set it equal to 0, that gives you the minimum value, which is what we're looking for, the minimum cost of wax. Well, it turns out that minimum value is the square root of 2 times the side length divided by 4. I know this because we just did it in class a week ago, and I can remember it. And that, as it turns out, is the exact dimension that the bees use. They don't use too tall and too skinny. They use the square root of 2 times s divided by 4. And so there's been scientists studied it since the 1600s. They studied this honeycomb, and it wasn't really until calculus that they would do this. I think it's amazing that bees do that all on their own and make a very optimal structure. The other thing that's interesting about the hexagon cells is that there is a movie out. You can find it on YouTube if you just Google Mathematics of the Honeycomb, and there's a couple of excerpts from a movie that was made on it in the late 60s. Old technology, but very good photography. And they explain that in that movie they take some different cells that share sides, because one of the reasons the bees minimize the wax is every side is shared by 2 cells, so that cuts the cost in half. And they're super thin too. But if they put squares all together, they also share the sides, but they would use a little more wax. And if you hang a weight on it, and honey is very heavy, if you hang a weight on it, it puts all the stress wherever the weight is. And so it breaks easily. When you do the same thing with a hexagon, and they have an instrument they show in this video where they can show the stress gets perfectly distributed up through the hexagon mesh. So it hangs there with the weight distributed evenly, and therefore a given amount of wax or the structure is able to hold a much greater amount of honey. And any beekeeper will tell you that, yes, it's heavy. I understand it's 40 or 50 pounds for one of those little things, and yet the structure is able to hold it very well. So it's an optimal engineering problem. I actually had a student quit after one day with a problem because she thought the math was too complicated. I said, the bees do that all on their own. They don't quit, and you shouldn't quit until just because it's a little tricky. But it's very interesting problem, very fascinating.
That is absolutely incredible. And what's even further amazing is that those little bees do that in the dark with such geometric precision.
Yeah.
That just shows to the glory of God's creations.
Yes, it is.
So,
yeah, I had told my when I show the class, we figure out how much wax they save, and it's only like in the third or fourth significant digit. They don't save much wax. So I said, why would they do that then? If they don't really, why not just make them square? Why not just make the side square? And I really think God is just showing off a little bit, showing what he can do.
And he has every right to, because that's pretty cool.
Yeah, and it's part of what it says in Romans. It says the invisible things of creation shout out of God's glory, and so that we're without excuse.
Amen.
And so it's just another of many examples throughout nature that say, wow, there's a very smart person behind all of this.
That's right.
Intricate designs.
Exactly, divine creation, truly.
Yeah.
Thanks, Gene.
Sure,
that was
thanks.
fascinating. I am impressed.
All right.